Hello, so this is a revision video for AP Chemistry 7.10, Reaction Quotient and Le Châtelier's Principle. Le Châtelier's principle describes how a system at equilibrium responds to stress. The reaction will shift to oppose the change and re-establish equilibrium. We can predict the direction the system will shift in by using the reaction quotient Q for the reacting system and the equilibrium constant K for the reaction. Remember, K, the equilibrium constant, Kc or Kp, is the ratio of product to reactant concentrations at equilibrium, whereas Q, the reaction quotient, is the ratio of product to reactant concentrations at any moment in time, even if the system isn't at equilibrium. When a system is disturbed or stressed, if the reaction quotient Q is smaller than K, the system will shift right to form more products, and Q will slowly get bigger again until it equals K and the system is at equilibrium again. If the value of Q is greater than K, the system shifts to the left to form more reactants. The value of Q gets progressively smaller until eventually it equals K and the system is at equilibrium again. Remember, when Q equals K, the system is at equilibrium. So if a system at equilibrium is subjected to a change or stress, but Q continues to equal K, then no shift will occur. Exam tip here, you can kind of think of Q as telling us where the reaction system is at any moment in time, and K telling us where it's going to go. So Q being the ratio of product to reactant concentrations at a given moment in time, and K being the proportion of product to reactant concentrations at the end, when the system reaches equilibrium. So how does this link to Le Châtelier's principle? Well, when a system at equilibrium is disturbed, what we really do is we change the value of Q compared to K. For example, if a reactant is added to a system at equilibrium, the denominator in the Q expression increases, meaning the value of Q decreases. And as we've just seen, this means equilibrium will shift to the right. Equally, if a product is added into a system at equilibrium, the product concentration increases, so the numerator in the Q expression increases. This means Q increases in value, and as a result, equilibrium shifts left. Changes in pressure and volume for gas-based systems affect QP in the same way as QC. Temperature changes are slightly different because they actually change the value of K rather than Q. For example, for an endothermic reaction direction, increase in the temperature increases the value of K. The system shifts to the right. For exothermic reactions, increase in temperature decreases K and the system shifts to the left. When the temperature is initially changed, Q remains the same because we aren't changing the concentration of products or reactants, we're just changing the temperature. But because K has changed, the system is now out of equilibrium. Q doesn't equal K. And as a result, the concentrations of everything in the system will have to change to make sure Q equals K again. And now we can predict the change that will occur based upon the same rules as before. If Q is smaller than K, equilibrium will shift to the right, favors the forward direction, or if Q is greater than K, equilibrium will shift to the left and favor the reverse direction.